Hi, my name is Markus, and together with my colleagues we developed this TLS, a scalable active scanner that collects TLS server configurations and that can be used for TLS fingerprinting. So why should we care about TLS configurations? Well, analyzing them can help to secure the internet. How? If you have a look at the TLS ecosystem, we see it's very complex and heterogeneous, with countless unique TLS configurations out there. And with active measurements, we can collect them and analyze them on a very large scale. This has potential to be used for further data mining applications, like revealing malicious activity on the internet. And for example, two related works have already found malicious command and control servers through active TLS fingerprinting, where their fingerprint is basically just a textual representation of the TLS configuration on the server. And they basically found out that they can use certain fingerprints to indicate something like a normal Apache web server or even a malicious command and control server. However, such data mining applications can only be as good as the underlying data. And if we have a look at related work and how they collect this data, we basically see two main strategies. The first one uses static requests to collect this data. The main use case would be just fingerprinting. With approaches like YARM or active TLS stack fingerprinting, we shorten to ATSF in this work. And their scanning is very lightweight to be scalable. And they achieve this by using just 10 fixed requests per server. However, using just 10 requests will always limit the data you're able to collect. But there's a second strategy out there that utilizes a TLS stack model to guide the scanning. The main use case currently is just single server debugging with tools like SSLice or TestSSL. And their scanning is really resource intensive, using hundreds of requests per server. However, they are able to collect the maximum amount of data that is possible to collect, at least according to their model. And with this TLS, we propose an approach that utilizes such a TLS stack model and is still efficient enough to be used on a large scale. And we investigated the following research questions. First of all, how should we define a scanner that utilizes such a TLS stack model? Secondly, what is the scanning effectiveness of all the mentioned scanners? Third, how do the scanners perform regarding a malicious server detection? And lastly, what are common TLS parameters? Let's start with the TLS scanner and model. You can see an abstract overview of the scanner we developed on the left side and a TLS server we want to scan on the right side. And ultimately, we want to get this TLS configuration hidden somewhere inside the server. But we cannot get it directly, we cannot only measure its effects. So we need something on our side that interprets these effects and allows us to reconstruct the full configuration. And that's our TLS stack model. Basically use this model to now create new client hellos that most likely will reveal new information from this server. We send this to the server and the server reacts to it somehow depending on its TLS configuration. And then we just update our TLS stack model with the information we have learned. And then we repeat this process until we do not learn any new information. Let's have a look at an example how this works for cipher suits. So basically the model just says, well, a server supports a list of cipher suits and there are priorities among these ciphers. And to scan them, we just put all the ciphers we are aware of into a single client hello and send it to the server. Then the server selects a single cipher as response and then we know, well, this is the top one priority of the server. Then we update our model with this information and generate a new client hello. In this case, it would be just almost the same client hello as before, just the one cipher suit is missing. And this means the server needs to select its second priority. And we just repeat this process until the server stops responding. Now, let's have a look at the effectiveness of the different scanners and if the TLS approach actually provides a benefit over related work. So first of all, how should we measure and compare an ability to extract TLS information? It's a quite abstract question. But we thought about the following. Given we have two different TLS server configurations and we scan them both with a scanner, without looking into the result of the scanner, if the two results are different, we know the scanner was able to collect the relevant piece of data. Keeping this idea in mind, we designed the following experiment. We just systematically permuted engine X TLS configurations in a local environment and scanned them all. And here you can see our results. You can see that this SAC TLS was the scanner that was able to detect all the configurations we have generated. This was actually not that surprising because we also used this environment during development. However, also TestSSL was able to detect almost all the configurations. Although active TLS stack fingerprinting as a slice and JARM performed quite poorly in this experiment. And the whole experiment was of course a bit artificial, so we repeated it on actual servers on the internet. So we scanned the top 10,000 Tranco domains. And here you can see the results. In this case, we don't have a ground truth anymore, so we can only show you the absolute number of configurations we have collected. And here you can see that the 3 scanners that utilizes such a TLS stack model really outperform the 2 fingerprinting approaches using just this static request. And yes, this SAC TLS was actually the scanner that collected the most configurations. However, this was not the only thing we evaluated. We also measured how many client hellos each scanner needed to send to each server to collect this information. And you can see that 2 fingerprinting approaches are really the most efficient ones. However, also this SAC TLS performs quite good using just 24 client hellos on average per server. And basically from this study, we concluded that we can use this SAC TLS, active TLS stack fingerprinting and JARM on a larger scale because they are efficient enough. And this was exactly what we did in the following study, where we scanned the Tranco top 1 million top list and the 2 block lists from AbuseCH listing command and control servers. And we scanned these servers for several weeks. In total, we collected 50 million data samples over 9 weeks for each scanner to compare a CNC detection and evaluate TLS parameter usage. Let's start with the CNC server detection. We basically just compared the ability of the 3 scanners to detect potentially malicious servers. And we did like the following. We basically just counted how often we saw a specific scanner output previously from command and control servers versus from top list servers. And this resulted in a score between 0 and 1, how certain we are that we found a command and control server. And then we basically just classified all servers that had this scanner output and a score above a certain threshold as CNC server, which is basically just a binary classification. And using this binary classification, we can show you the following metrics from the results. On the left side, the precision, and on the right side, the recall. So precision is basically just a metric that shows you the rate of how many of our classifications were correct, depending on the threshold. And the recall is basically just a rate of how many of the command and control servers in our dataset we were able to detect, depending on the threshold. And you can see that this SAC TLS and active TLS stack fingerprinting actually performed quite similar. Only for the higher thresholds, where the precision reaches a value above 99%, we can see that this SAC TLS had a higher recall. So this means that in these cases, this SAC TLS revealed the more finer details necessary to detect some of the CNC servers. However, no scanner was able to detect all the CNC servers. Now let's also have a look at the TLS parameter usage. Because this SAC TLS can not only be used for fingerprinting because it produces a human-readable representation of the TLS configuration, we can use it to analyze the TLS parameter usage in the internet. As an example, we added here a statistic about the support for the different TLS versions we saw. You can see that the majority of servers still support TLS 1.0 and 1.1, although they are considered deprecated. Almost all servers support TLS 1.2, and around 3 or 4 servers support TLS 1.3. Interesting was that very few servers actually did not abort the handshake when they requested a version they did not support, but they downgraded the version to a lower version. And with this, I'm already at the end of today's talk. So to conclude it, we introduced you to the dissect TLS scanning approach, which is both exhaustive and scalable. We compared the effectiveness and resource usage of scanners in a local testbed and on topless servers. We compared a CNC detection, where the results revealed that dissect TLS had a similar precision, more than 99%, as active TLS fingerprinting, but had a 2.8 times higher recall. Further in the paper, you can find a more detailed description of the TLS stack model and how we scanned it, and find additional TLS parameter statistics. Overall, we think dissect TLS challenges current active TLS fingerprinting approaches while additionally producing a very valuable dataset. And of course, we open sourced all our data and code under the following link. Thank you very much.